All right, welcome to the Explainer. Today, we're going to crack open this tiny little device that, no joke, powers our entire modern world. It's a microscopic genius hiding in plain sight, probably in the very device you're using to watch this. Okay, let's kick things off with a big question. I mean, a really big one. If you had to pick the single most important invention of the 20th century, what would it be? It's a tough call, right? There are so many contenders for that top spot. Your mind probably jumps to some of the heavy hitters, right? Maybe the printing press for spreading knowledge like wildfire, or penicillin, which literally saved millions of lives. Heck, maybe even nuclear power, unlocking the atom itself. And you know what? You'd have a fantastic argument for any of them. But what if I told you that the real unsung hero, the thing that makes your phone, your laptop, the internet, all of it possible, is something you can't even see? Well, that's the transistor. And today, we are going to dive deep and figure out exactly how this microscopic marvel actually works. So here's the game plan. We're going to break down a really important type of transistor called the bipolar junction transistor, or BJT for short. We'll cover why it's such a big deal, what it's made of, its secret sauce for controlling electricity, its kind of split personality, and finally, how we get it ready to do all its amazing work. All right, let's jump into section 1, the unsung hero. First things first, let's just take a moment to really appreciate why this little component is so incredibly fundamental to, well, everything we do. Okay, so what is a BJT at its core? It's what we call a semiconductor device. That means it's made from a material that's, well, it's not a great conductor like copper, but it's not an insulator like rubber either. It's somewhere in the middle. And that special property is what lets it act like a super sophisticated, highly controllable gate for electricity. It's got 3 connection points, and the real magic, the whole trick, is how a tiny, tiny signal on one of those points can control a much, much bigger flow of electricity through the other 2. So you're probably wondering, what is this thing actually made of? It's definitely not just a piece of wire. The way it's built is incredibly clever and deliberate, and it's the key to everything. So let's take a look inside what's basically a 3-layer sandwich. So, the BJT is built from 3 layers of a semiconductor material, usually silicon. But these layers are specially treated, a process called doping. All that means is we add some tiny specific impurities to change how they conduct electricity. First, you've got the emitter, which is heavily doped so it can supply a whole flood of charge carriers. Then you have the collector, which is set up to, well, collect all those carriers. And right in the middle, sandwiched between them, you have the most important part, the base. And this little 3-layer sandwich actually comes in 2 main flavors, NPN and PNP. The names sound a bit technical, but they just describe how the layers are doped. See, N-type material has extra electrons ready to move, while P-type material has little gaps, or holes, where electrons could fit. So an NPN transistor is just a thin P-type layer squeezed between 2 N-type layers. And a PNP? You guessed it, it's just the opposite. This whole arrangement is what tells the electric current which way to flow. Now here's the really brilliant part, the absolute genius of this design. It's all about that middle layer, the base. It's intentionally made to be incredibly thin and only very lightly doped. I mean, it seems like it's the weakest link in the chain, right? But that seeming weakness is actually the secret key to the transistor's most powerful ability. And that brings us perfectly to the BJT's most famous trick, amplification. This is the magic where a teeny tiny signal can be used to control a much, much larger one. You know, the best way to get your head around this is with a simple analogy. Just picture a huge water pipe with a ton of water pressure just waiting to burst through. That's like the big current that wants to flow from the collector to the emitter. Now the base, that's like a tiny little control knob on a valve and not pipe. It only takes a tiny little twist, a small bit of current into the base, to open that main valve and unleash a massive but perfectly controlled flow of water. So how on earth does it do that? Well, it goes back to that super thin, lightly doped base. Because it's so thin, more than 95% of the charge carriers that get shot out from the emitter, they don't even have a chance to do anything in the base. They just zip right across it and get swept up by the collector on the other side. It's almost like they just fly right over it. And that, right there, is the whole principle of current gain. A tiny trickle of current coming into the base controls a huge, proportional river of current flowing through the collector. This is exactly how we can take a faint, weak radio signal from the air and boost it up into powerful, clear music coming out of your speakers. Okay, so this incredible ability, controlling a big current with a small one, it gives the BJT two main ways of working. You could almost say it has two different personalities. See, by changing the voltages we apply to it, we can basically tell the BJT what to do. In what's called active mode, it works like that amplifier we just talked about, that precise control knob. But there are two other modes, saturation and cutoff. And in those, it acts like a simple light switch. In saturation, the switch is flipped all the way on, and in cutoff, it's completely off. So here's the really crucial takeaway. This one single tiny device is the foundation for two completely different worlds. It's the precise, variable controller you need for analog stuff, like a great audio amplifier. And it's also the simple on-off switch that creates the binary logic, the ones and zeros, that power every single digital computer on the planet. It's incredible. But here's the thing. A transistor, as brilliant as it is, it's kind of like an amazing actor. It can't just perform in a vacuum. It needs a stage, it needs a director, it needs to be set up perfectly within a circuit to do its job. And that whole setup process, it's called DC biasing. It's really just about applying the right, steady DC voltages to get the transistor into the correct mode for whatever we want it to do. This sets up what engineers call its operating point, basically getting it prepped and ready for action. So why is this so important? Well, think of it like tuning a guitar before a big show. If you don't do it, the transistor's performance is going to be unstable, unpredictable, a total mess. The signal might get all distorted, or it might not amplify anything at all. So, proper biasing, which we do with a few carefully chosen resistors, is what makes sure you get beautiful, clear music instead of just a bunch of noise. So the BJT literally taught us how to control the flow of electrons. And with that knowledge, we built our entire modern world. It's an absolute masterpiece of control. But here's the big question to leave you with. As these components keep shrinking, getting down to the size of just a few atoms, what happens when the thing doing the controlling becomes as small as the electrons it's supposed to control? What's the next leap forward?